Very good afternoon to friends in India, and good morning to our friends from Europe, and good evening to our speaker and other people from Japan or Paris. It's really my pleasure to welcome all of you to this webinar series. Today we have Professor Kenichi Uchida from National Institute for Material Science, NIMS, popularly known from Tsukuba in near Tokyo, in Japan. And you all know him. And I'm really grateful to Professor Uchida that he accepted our invitation. So on behalf of my team, co-convener Dr. Brajbhushan Singh, my other colleagues, Puspendra, Sakti, Ajay. So I really thank, and on behalf of the audience, and this is the 64th lecture of our webinar series. Now I see video of Professor Sabal Basu, so very nice to see you. He has become a regular listener these days. Really nice to have you. So a brief introduction about Kenichi Uchida. I mean, he is very well known in the field of spin caloritronics. He has discovered many novel effects, which others are really following, and very nice contribution to spintronics. So, brief academic career about him. He has obtained his PhD in physics from Institute for Material Science or Material Research, popularly known as IMR, at Hope University in 2012. Then he did assistant professorship also at IMR in Tohoku from April 2012 to 2014. Then he was an associate professor also at IMR in Tohoku University between 2014 to 2016. And since 2016, he has been the group leader for the Spin Caloritronics group at the Research Center for Magnetic and Spintronic Materials at National Institute for Material Science, NIMS. And he's really doing nice work. And he is also having a cross appointment as a professor at the Institute for Material Research since May 2019. I think when I was there and we attended the same faculty meeting, it was very nice. So he has got many awards and honors to his credit. I will read a few of them. In 2011, he got the JSPS Ikushi Prize, that is by Japan Society for the Promotion of Science. In 2013, he got the Condensed Matter Science Prize. 2013, he got the Young Scientist Prize. Commendation for Science and Technology by Minister of Education, Culture, Sports, Science and Technology. In 2014, he got the Gottfried Wagner Prize by German Innovation Award. Also in 2014, Nagas Prize, Frontier Ceylon Foundation. The same year, he got the Yamato Scientific Award by Yamato Scientific Corporation Limited. In 2015, he got the NISTEP Award, that National Institute of Science and Technology Policy. In 2019, he got the Funai Research Award. Also same year, he got the Marupun Research Encouragement Award. Also in the same year, he got WCC Special Recognition Award by World Cultural Science. And 2020, very important, he got the JSPS Prize, Japan Society for the Promotion of Science. And recently again, he got the Noguchi Chitagao Award by the Noguchi Institute. So he is working on several interesting topics. I'm sure he will tell that today in his lecture. So with this brief introduction, I again welcome you, Kenichi, for this seminar, and I request others, please mute your microphone and speak camera during the lecture. We don't take any questions during the lecture. If you have any questions, kindly write in the chat box or raise your hand or just say I have a question. At the end, we will take all these questions. Thank you. It's all yours, Kenichi.
Okay, thank you very much for the kind introduction, and I will share my slide. Okay, can you also see my laser pointer? Okay.
Yes.
Okay, thank you very much for inviting me to this special webinar. So my name is Kenichi Uchida from National Institute for Material Science in Japan. First of all, I appreciate Professor Vedanta for giving me this opportunity and for organizing this webinar. So here I talk about our recent progress on the transverse thermoelectric conversion based on spin caloritronics. The transverse thermoelectric effect refers to the conversion of a heat current into a transverse charge current and its reciprocal effect, which appear in a magnetic conductor under a magnetic field or in a magnetic material with spontaneous magnetization. Such phenomena in magnetic materials have been receiving increased attention from the viewpoints of fundamental physics and thermoelectric applications. I would be happy if you are interested in this topic. So before moving to the main talk, let me briefly introduce our institute, research center, and group. NIMS is one of the National Research Institute in Tsukuba, and its location is relatively close to Narita International Airport, relatively close to Tokyo. NIMS was established in 2001 by merging two research institutes, and its objective is to carry out fundamental research and generic infrastructure technology research and development in the field of material science and technology, with improving the level of material science. And so basically, NIMS covers all the categories of the material science and consists of 8 research centers or divisions. One of them is the Research Center for Magnetic and Spintronic Materials, and my group, called the Spin Caloritronics Group, belongs to this center. Our research center consists of 7 groups, which covers both application research and fundamental physics research in spintronics and magnetics. Especially the application part is very strong. Many members are devoted to develop high-performance magnetic sensors and memories, and to create excellent permanent magnet materials. Among them, my group is called the Spin Caloritronics Group, which was established when I joined NIMS in 2016. Our research topic is substantially different from the other groups. So we are trying to create new science and technology for thermal energy engineering based on spin electronics, which were impossible with conventional electronics alone. My group size is like this, relatively small, although this group photo is a bit old. So now the Spin Caloritronics Group consists of 2 permanent staffs. I am the Dr. Iguchi, and 3 postdocs, including the JSPS fellow, and student and technical assistants. So we have a close appointment partnership with Professor Seki in IMR Tohoku University. And in addition, I also have an adjunct position in the University of Tsukuba, and we can accept the student applications. So here, I would like to take this opportunity to thank all the collaborators for their support and contribution. In particular, in the main topics shown today, our group member, Dr. Iguchi, Dr. Modak, and our past members, Dr. Asuka Miura and Kaoru Yamamoto, made a significant contribution. And the main work was also conducted in collaboration with Dr. Sakuraba's group and Dr. Yoshio Miura's group in NIMS. Here, Dr. Joe made a good, very important contribution. I also acknowledge many collaborators for their contribution, and JST Crest project for the financial support. Okay, so this is the outline of my talk. After a brief introduction on spin caloritronics, I will explain the thermoelectric effects unique to magnetic materials. Among such magneto-thermoelectric effects, the anomalous nernst effect is the most popular and actively investigated. I will show the fundamentals and recent research trend on this effect. So then I will show our recent progress on its reciprocal effect called the anomalous etching thousand effect. And to improve the thermoelectric performance of the transverse thermoelectric conversion, we have also recently demonstrated conceptually different transverse thermoelectric conversion appearing in hybrid materials. I will show the details on this topic, followed by summarizing this talk. Then let's start from the introduction. As is well known, the thermoelectric effects enables the interconversion between charge and heat currents. And there are various thermoelectric effects as shown later, but most studies in thermoelectrics have mainly focused on the some power generation based on the Zebic effect, which converts a heat current into a charge current, and the electronic cooling based on the Peltier effect, which converts a charge current into a heat current. And independently from the very strong activity in thermoelectrics, in the past few decades, extensive studies on spintronics have been carried out all over the world, where the electron spins are exploited as new information and energy carriers in addition to electron charge. So as presented by many speakers in this webinar, spintronics has led to important scientific discoveries and industrial applications. And its key concept, one of the important key concepts is spin current, which is a pure flow of spin without accompanying a charge current. In this stream, the interplay between spin, charge, and heat currents have been actively investigated, and a wide variety of physics and functionalities have been discovered. For example, in addition to the Zebic and Peltier effects, various thermoelectric effects appear in the magnetic material depending on its spontaneous magnetization, which are called the Magneto thermoelectric effects. The interconversion between heat and spin currents is enabled by the thermospin effects, such as the spin Zebic and spin Peltier effects. The fundamental physics and application studies on such novel phenomena are the main topics in spin caloritronics. As shown here, an annual international workshop on spin caloritronics has been held since 2009. However, considering the pandemic situation, the workshops in 2020 and 2021 have been cancelled. Even in this difficult season, the spin caloritronics research is still active, and I hope that we can restart the workshop from 2022. Here I summarize the history of spin caloritronics. The word of spin caloritronics was used for the first time in this theoretical paper published in 2007. Here, the effect of a thermal gradient on magnetization dynamics was discussed theoretically. One of the triggers for the rapid development of spin caloritronics is the discovery of the spin Zebic effect, which refers to the generation of a spin current as a result of a heat current in magnetic materials. This is a spin version of the Zebic effect. In 2010, the spin Zebic effect was found to appear not only in conductors, but also in insulators. This clearly showed that the spin Zebic effect is conceptually different from the conventional thermoelectric effects driven by conduction electrons. To clarify the mechanism of the spin Zebic effect, many researchers began the studies on spin caloritronics. Several years later, a spin version of the Peltier effect was also discovered, which is reported by Professor Van Beek's group in Groningen University. And this phenomenon is the generation of a heat current as a result of a spin current. In 2016, we have established the versatile measurement method for the spin caloritronic phenomena that output heat current, which provides a new direction in this field. This slide shows only a specific aspect of the spin caloritronics history, but with these discoveries, physics studies on spin caloritronics have been accelerated. After this report, we are investigating different spin caloritronic phenomena by using this established technique as shown later. So the diversity of spin caloritronic phenomena partially comes from the fact that spin currents are carried not only by conduction electrons, but also by spin waves or magnons, and other various energy carriers having the spin angular momentum. Even if we focused on electron transport.
नीचे नेटवर्क नहीं आ रहा ना सर के पास है सर नहीं सुन रहे मुझे तो बोल के गए भेज लिंक
I'm sorry, somebody was speaking. I am muted. Please mute your microphones. Okay, Kenichi, please continue.
Okay. Okay. Even if we focused on the electron transport in spin polarized electron system, the conventional 2x2 transport matrix for spin and charge conversion is extended into a 3x3 matrix owing to the conduction electron spin currents, resulting in the appearance of many spin caloritronic phenomena contributing to each off-diagonal component of this matrix. Furthermore, by adding the magnon spin current, more various phenomena can appear. The important point here is that basically the input and outputs in experiment are the heat or charge currents. So therefore, although there are various phenomena, spin caloritronic phenomena result in thermoelectric conversion through various interaction and conversion phenomena. So, for example, the spin Zebic effect refers to the conversion from a heat current into a magnon spin current, which is mainly investigated in the junction comprising a magnetic insulator and paramagnetic metal. The generated magnon spin current is then converted into a conduction electron spin current through the spin mixing conductance at the junction interface. The conduction spin current is subsequently converted into a charge current due to the spin orbit interaction or spin Hall effect. Therefore, the spin Zebic effect and the spin Pelch effect are essentially the energy transport via the interfaces, and in fact, the improvement of thermospin conversion properties by interfacial engineering has been reported. So on the other hand, the main focus of this talk is the direct thermoelectric conversion between charge and heat current using magnetic materials. A spin current is not the direct driving force here, but spin causes the thermoelectric conversion to exhibit a variety of behaviors and symmetries. Here I show the transport phenomena in magnetic materials, not only in electric and thermal transport properties, but also thermoelectric conversion properties depends on the direction of magnetization owing to the concerted action of spin polarized electron transport and spin orbit interaction. Such phenomena can be classified into two types. One is the longitudinal effect, in which the input and output current flow parallel to each other. The other is the transverse effect, in which the input and output currents flow perpendicular to each other. These phenomena have been known for a long time, but actually some of them have not been sufficiently investigated. So by reviewing them from the modern eyes of spin caloritronics, these phenomena become a very active research subject. So in this talk, we mainly focused on the transverse thermoelectric conversion in magnetic materials, namely the anomalous nernst effect and the anomalous etching Southern effect. So the first topic is the anomalous nernst effect. The anomalous nernst effect refers to the generation of thermoelectric voltage in the direction perpendicular to both an applied temperature gradient and the magnetization in magnetic materials. Basic studies on the anomalous nernst effect has been carried out for a long time, but in the early days of spin caloritronics, the development of experimental methods for separating the spin Zebic effect from the anomalous nernst effect was promoted all over the world. Therefore, the studies on the anomalous nernst effect have also been activated. In particular, since the observation of the giant anomalous nernst effect in magnetic topological materials, the studies on this effect has accelerated further and becomes one of the big trends in condensed matter physics. The transverse thermoelectric effects have unique symmetry and scaling law completely different from the conventional Zebic effect. Therefore, the transverse effects have a potential to realize simple and versatile thermoelectric applications. A typical Zebic device have a complicated structure in which p-type and n-type semiconductors are arranged alternately and connected in series. Since the direction of the charge and heat current is parallel to each other, a certain thickness is required to create a temperature difference. On the other hand, in the anomalous nernst effect, heat and charge current flows perpendicular to each other. So a simple sheet structure works as a thermoelectric device. and its output is proportional to the device area. Output power is proportional to the device area, and output voltage is proportional to the length of the along the electric field. So even when making a thermopile element to enhance the voltage, as shown here, a simple in-plane zigzag structure is sufficient. So a thermopower can be also obtained by winding a wire around the pipe-shaped heat source and directing the magnetization along the actual direction. Oh, sorry. Here is merit of the anomalous nernst effect, but the output thermopower is still small, so the performance improvement is very important. So here I show how to measure the anomalous nernst effect in the case of bulk materials. The anomalous nernst effect can be measured simply by applying a temperature gradient and a magnetic field and to magnetic materials and measuring the thermopower in the direction perpendicular to them. In contrast, in the case of thin films, due to the huge difference in the thickness and in-plane dimensions, the measurement setups are classified into two categories. One is called the in-plane magnetized configuration, where the thin film is magnetized in the in-plane direction and the temperature gradient is applied in the normal direction of the film. This setup is suitable for energy harvesting because it works simply by attaching a film or sheet on the heat source. On the other hand, it's difficult to quantify the temperature difference between upper and bottom lower surfaces of the thin films. Therefore, the experiments in the in-plane magnetized configuration is not suitable for the quantitative estimation of the anomalous nernst coefficient. The other setup is called the perpendicularly magnetized configuration, where the film is magnetized in a normal direction of the film surface, and the temperature gradient is applied along the in-plane direction. In this case, it's easy to estimate the temperature difference in the sample, and the anomalous nernst coefficient is usually quantified in this setup. Here is an example of the experimental results of the anomalous nernst effect in each setup. Here we used iron platinum multilayer film, and as this symmetry shows, the thermoelectric voltage shows an odd dependence on the magnetic field, and when the magnetization is saturated, the thermopower is also saturated. The odd dependence on the magnetic field is a common behavior of all the transverse thermoelectric conversion. To take advantage of the anomalous nernst effect, we have recently demonstrated the construction of anomalous nernst thermopile using a single material. As shown in the left illustration, although the anomalous nernst thermopile has a simple lateral structure, a junction structure comprising two different materials are necessary. Because the anomalous nernst voltage is cancelled out in a single material with zigzag structure uniformly magnetized. So to overcome this situation, we used helicity-dependent all-optical switching of magnetization, which enables local and reversible control of magnetization by irradiating a sample with circularly polarized light. So by alternately reversing the magnetization direction, we can avoid the cancellation of anomalous nernst voltage in the single material. A single material works as a thermopile. We have clearly demonstrated this concept experimentally. However, the obtained thermopower is still low. So the principal elucidation and material development for higher thermoelectric output is necessary. So what determines the anomalous nernst effect? The anomalous nernst coefficient consists of several transport coefficients, and all of them can be determined experimentally or by first principles calculations. First term is obtained is often regarded as an intrinsic part of the anomalous nernst effect because it originates from the transverse thermoelectric conductivity alpha xy, which directly converts a temperature gradient into an electric field. A research trend in improving the anomalous nernst coefficient is to find material with large alpha xy, in which the very curvature of the electronic bands near the Fermi energy plays an important role. The second term is attributed to the concerted action of Zebic effect and the anomalous Hall effect. Here, the longitudinal charge carrier flow driven by the Zebic effect is bent due to the anomalous Hall effect. The second term is small in many magnetic materials. However, this term will be important in the last section of my talk. These graphs show the anomalous nernst coefficient and transverse thermoelectric conductivity for various magnetic materials reported so far. The coefficient is often compared in terms of field-dependent magnetization rather than the saturation magnetization. However, since the anomalous nernst effect and related transport properties are estimated for uniformly magnetized materials, it's natural to compare the coefficient in terms of saturation magnetization, not simple magnetization. As shown here, the large anomalous nernst coefficient was obtained in Heusler compounds, such as cobalt-2 manganese gallium, CMG. As far as I know, the record high alpha XY was obtained for samarium cobalt type 5 type magnets at room temperature. Importantly, these parameters have no correlation with saturation magnetization in many materials. This is partially due to the fact that the intrinsic mechanism plays an important role in the anomalous nernst effect. Through these activities, the thermoelectric performance of the anomalous nernst effect have been improved dramatically in the past few years. Okay, next I will show our recent progress on the reciprocal process of the anomalous nernst effect. The anomalous etching Southern effect refers to the generation of a heat current in the cross-product direction of magnetization and the charge current in the magnetic materials. This symmetry means that the direction and magnitude of the heat current can be actively controlled by changing the magnetization direction. This phenomenon has also been known for a long time, but its magnetization was reported, its observation was reported nearly 1 century ago using bulk ferromagnetic materials. However, the quantitative estimation of the transport properties, transport coefficient, and the separation of the magnetization-dependent components from the field-induced effects were not reported. Since then, no experimental studies have been reported. This situation was changed by this work, which was done in collaboration with Professor Seki and Professor Takanashi in IMR talk. This method here now the anomalous etching Southern effect can be freely observed owing to the development of thermoelectric imaging method called the lock-in thermography technique. This method was made possible to evaluate the anomalous etching Southern effect not only in bulk materials but also in thin film devices. So here I briefly explain the lock-in thermography. This method provides a much better signal-to-noise ratio and higher sensitivity than the conventional thermography. So during the measurements, we applied a periodic external perturbation to the sample and extract the first harmonic response of the thermal images oscillating with the same frequency as the perturbation. The obtained thermal images are converted into lock-in amplitude and phase images by the Fourier analysis. Here, the amplitude image shows the distribution of the magnitude of the temperature modulation induced by the external perturbation, and the phase image provides the information about the sign of the temperature change, as well as the time delay due to heat diffusion. So to realize the direct observation of the anomalous etching Southern effect, using this technique, we measure the spatial distribution of the infrared radiation thermally emitted from the surface of the sample while applying a square wave modulated AC charge current to the sample. Here, importantly, the offset of this AC current should be 0. And by extracting the first harmonic response, we can separate the contribution of thermoelectric effects from the contribution from the Joule heating, because the Joule heating generated by this AC square wave modulated AC charge current is constant in time. So only the thermoelectric contribution can be detected. So by combining this technique with the magnetic field dependent measurement, we can visualize the temperature distribution induced by the anomalous etching Southern effect. So also by using this the same method, we also reported the observation of the spin-Peltier effect, anomalous anisotropic Magneto-Peltier effect, and the Magneto-Thomson effect. Also, I omit the detailed explanations on these phenomena. Here, I would like to emphasize that the lock-in thermography technique is applicable to the measurements of various heat generation phenomena. And now this method is a powerful tool to investigate the behaviors and functionalities of the spin caloritronic phenomena. So this unique symmetry of the anomalous etching Southern effect enables the active heat current control, such as the directional or on-off switching of heat current. So this is one of the examples of such demonstrations. By combining the anomalous etching Southern effect with magneto-elastic coupling, we demonstrated that the heat current direction can be rotated simply by applying a strain to ferromagnetic metal films. So this is because the magneto-elastic coupling changing the magnetic easy axis direction from perpendicular to in plane. We also demonstrated the electric field induced on-off switching of heat current, which is based on the combination of the anomalous etching Southern effect and the electric field effect on magnetism. In addition to these demonstrations, we have also demonstrated a new functionality called magneto-optical design of heat current, which is based on the combination of helicity-dependent all-optical switching of magnetization and the anomalous etching Southern effect. By using this technique, okay, let me continue. Okay, by combining these effects, various heating and cooling distribution can be designed by illuminating the magnetic material with circularly polarized light. So as shown here, the anomalous etching Southern effect enables various active thermal energy engineering. So this is the experimental result that obtained from the same sample. And by using the magneto-optical recording technique, we can design the temperature modulation as shown here. Okay, let's go back to this slide. So up to now, we have introduced the advantages and the unique functionalities of the anomalous nernst and etching Southern effects. However, these phenomena are currently far from practical applications because the anomalous nernst coefficient is still much smaller than the Zebic coefficient of materials not used nowadays. The current record high value of the anomalous nernst coefficient at room temperature is still smaller than 10 microvolt per Kelvin, while Dr. Sakuraba in NIMS estimated at least 20 microvolt per Kelvin is necessary for heat sensing applications based on the anomalous nernst effect. So even for samarium cobalt 5 and CMG, cobalt manganese gallium, showing the large anomalous nernst effect, the dimensionless figure of merit is still in the order of 10 to minus 3. So the definition of the figure of merit for the anomalous nernst effect is very similar to that for the Zebic effect, where the Zebic coefficient is replaced with the anomalous nernst coefficient here. Therefore, the strategy for improving the figure of merit is also similar. The materials should have a higher thermal power and higher electrical conductivity and lower thermal conductivity. Many researchers are looking for new materials and principles to further enhance the transverse thermal power, and its reduction of the thermal power by nanostructuring or phonon engineering is also an important task, although such activity is quite limited. For example, if the transverse thermal power here is enhanced by 10 times from the current record high, and the thermal conductivity is reduced by half, the figure of merit can be greater than 0.1. So which is, this value is still very small. However, owing to the aforementioned unique functionalities, I believe that the transverse thermoelectric conversion with such improvement leads to various applications. To accelerate the material searching, we have recently developed a high-throughput screening method for the thermoelectric and thermospin conversion phenomena, combining a lock-in thermography technique with combinatorial material science. So by visualizing the temperature distribution modulation in the composition spread film, we can obtain the systematic and continuous composition dependence of the anomalous etching Hausen effect from a single sample. So we have especially Dr. Modak, one of the members in our group, have demonstrated the usability of this method by forming the epitaxial Heusler alloy film with a composition gradient. So importantly, this method is also applicable to searching material with high spin-to-charge conversion efficiency by measuring the spin pellicle effect. Therefore, this high-throughput screening method will accelerate the materials research on the interconversion between the charge, heat, and spin currents. Okay, so as an effort to enhance the thermoelectric performance, we propose the transverse thermoelectric generation driven by a mechanism different from the anomalous nernst effect. Finally, I will review this recent work. This work was done in collaboration with Dr. Sakuraba's group in NIMS, and Dr. Zhou and Dr. Yamamoto made a significant contribution in the experimental and theoretical parts, respectively. Okay. As discussed in the previous section, the anomalous nernst coefficient consists of two terms, and most of the recent studies focused on improving this first term. In this work, we were inspired by the second term and artificially engineered the contribution of the Zebic effect and the anomalous net Hall effect to drive the transverse thermoelectric generation. Here, please imagine a closed circuit comprising two different conductors. When the temperature gradient is applied to this circuit, a charge current is generated due to the Zebic effect, which is comes from the difference in the Zebic coefficients between these two materials, A and B. Actually, this configuration was used by Dr. Thomas Zebic 200 years ago when he discovered the Zebic effect. We replaced one of the material in the closed circuit with a magnetic material. Here, the Zebic-driven charge current is converted into a transverse electric field here by the anomalous Hall effect when the magnetic material is magnetized in the direction normal to the plane. As shown in these illustrations, the anomalous Hall effect driven by this Zebic effect in thermoelectric and magnetic hybrid materials enables the transverse thermoelectric generation with a similar symmetry to the anomalous nernst effect. We call this phenomenon the Zebic-driven transverse thermoelectric generation, STTG. So here, since the Zebic effect is the driving force, the Zebic coefficient of the thermoelectric material must be large, and the anomalous Hall angle in the magnetic material must be large. Okay, and the left figure shows an equivalent circuit of the hybrid material comprising thermoelectric and magnetic materials in the direction parallel and perpendicular to the temperature gradient. We phenomenologically formulated the transverse thermal power in this system and obtained this equation. The total thermal power is expressed as the summation of the anomalous nernst coefficient and the STTG contribution. The STTG term strongly depends on the factor called the size ratio defined here, and which is determined by the dimensions of the thermoelectric and magnetic materials. When the size ratio is very large, the STTG term is proportional to the anomalous Hall angle in the magnetic material and the Zebic coefficient in the thermoelectric layer. Here we plot the total transverse thermal power as a function of the size ratio for the typical combinations of the thermoelectric and magnetic materials. When the anomalous Hall angle of the magnetic layer is large, here we used assumed the quartz manganese gallium. The STTG contribution can be much greater than the anomalous nernst contribution, and its sign can be reversed when the sign of the Zebic coefficient is reversed. Sign of the Zebic coefficient of the thermoelectric layer is reversed. We found that the total thermal power, transfer thermal power, can be larger than 100 microvolt per Kelvin by optimizing the combination of magnetic and material and thermoelectric materials, and also by optimizing their dimensions, which this value is more than an order of magnitude larger than the anomalous nernst coefficient reported so far. To experimentally demonstrate the colossal transverse thermoelectric generation, we performed the power measurement using epitaxial cobalt-2 manganese gallium film fixed on various silicon substrate. The CMG film and the silicon substrate were separated by an insulating MgO substrate, and which can be connected electrically only around the ends of the sample. Here we show that magnetic field dependence of the thermal power without the electrical connection. It's natural that only the anomalous nernst effect was observed in this setup, and the result was irrelevant to the carrier type of the silicon substrate. Here we used N-type silicon, P-type silicon, and non-doped silicon. When the CMG layer was connected to the silicon substrate at the ends of the sample, the large transfer thermal power of more than 80 microvolt per Kelvin was observed to appear when the N-type silicon was used. The sign of the thermal power is reversed when P-type silicon with the opposite sign Zebic coefficient was attached. So when the magnetic thermoelectric layer is highly resistive, the obtained thermal power was not affected. All the experimental results are quantitatively consistent with our phenomenological calculations. So these plots, independent plots, are the experimental results, and these curves comes from the phenomenological calculation. This consistency confirms the appearance of the STTG contribution. The large STTG thermal power can be generated even in the absence of the magnetic field if magnetic material with finite remanent magnetization and finite coercive force are used. We demonstrated this feature by using L10 type iron platinum thin film with perpendicularly magnetized perpendicular magnetic anisotropy. In this study, we demonstrated the concept of the STTG using several typical materials. However, there are plenty of scope for the performance improvement based on the vast amount of studies on the Zebic and anomalous Hall effect. Although we focused on the transverse thermal power, the thermoelectric voltage in this experiment, our calculation also showed that the figure of merit can also be improved by the STTG. Okay, so finally, let me summarize my talk. Today, I reviewed the fundamentals of the spin caloritronics and reported our recent progress on the transverse thermoelectric conversion in magnetic materials, which has a simple and versatile device structure and exhibit unique functionalities that cannot be realized if only the conventional Zebic effect was used. So in addition to the phenomena discussed today, in addition to these phenomena, we also phenomenologically formulated the reciprocal process of the STTG, which means that the thermoelectric and magnetic hybrid materials can be used also for the transverse thermoelectric cooling. So future work includes the searching and developing magnetic materials with large anomalous nernst and Hall coefficient, and optimizing the combination of thermoelectric and magnetic materials and their dimensions for the STTG. In addition to the enhancement of the transverse thermal power, reduction of the thermal conductivity by nanostructuring or phonon engineering is also important. So to do this, the interdisciplinary fusion among spin caloritronics, nanoscale material science, and thermal energy engineering is desired. Okay, and that's all. So thank you very much for your kind attention.
Yeah, thank you so much, Kenichi, for this excellent overview of really nice topics. So on behalf of everyone, I thank you and clap on behalf of everyone. So before we take some questions, I would like to take a group photo of the audience whoever present. I request you to switch on your camera. We will take a group photo. Kenichi, can you please stop sharing your screen?
Okay.
Yeah, and I will just take a photo now. Okay. So smile. Now the next set of people. So many, okay. Many people have not, okay. I take some different. All right, thank you. So you can now switch off your camera, and Kenichi, you can share your screen so that we can take some questions. Yeah. So Mahindran has a question. Mahi, please go ahead.
Sorry. Hello, Uchida-san. So what is the maximum temperature difference between the opposite phases you get in the anomalous etching effect?
Yeah, actually, the output is very small. And actually, we haven't performed such a application type demonstration, but maybe in our measurement, the maximum temperature difference is still in the order of several tens of millikelvin, very small.
Oh,
But I think that by optimizing the device structure or device dimensions, not the generation of temperature difference of 1 Kelvin or something can be generated. But anyway.
But
yeah,
there are some previous works on the bismuth antimony alloys, I think in 1980s and 70s, where they could get a temperature of about 156 Kelvin. I think from a Japanese group, as well as I don't remember which other group is. So of course they didn't investigate the anomalous etching effect at the time.
Yeah. Exactly. The bismuth antimony or bismuth some alloys exhibit very large ordinary nernst effect under a strong magnetic field, and especially at low temperature. But the requirement of external magnetic field becomes a nuisance of the realistic applications. Yeah, so we are investigating the anomalous etching effect. It works in the absence of magnetic field, but the efficiency is still much lower than the ordinary nernst effect of bismuth alloys.
I see. Okay, thank you very much. Can I ask one more question?
Okay, go ahead.
Well, you talked about the change in the magnetic anisotropy. I think one of the slide on ferrofluxoelectric materials.
This one?
Yeah. So let me just see here. So you do apply electric field here, is it? To change the strain in the material?
In this case, actually, we modulate the Curie temperature of the cobalt film by the electric field effect. This is sorry, I didn't show any sample information here, but this sample is a bit special. So due to the redox reaction induced by the electric field, the Curie temperature of the cobalt film is drastically changed. So under the electric field application condition, this becomes paramagnet at room temperature. So the etching completely disappears.
I see. So that means that's close to the Curie. The sample is close to the Curie. I mean, the temperature is close to the Curie temperature of the material. Is it?
In this case, yes. But if we combine the kind of standard electric field effect that modulates the magnetic anisotropy, we obtain the functionality similar to this, even in the case of electric field effect.
I see. Okay, thanks very much.
Thank you.
Yeah, thank you for the nice talk. Yeah.
Thank you very much.
Yeah, thank you, Mahi, for your question. So maybe I will ask one question. So in slide 30,
30.
yeah. So you mentioned about this like device geometry. In reality, when you make such a device, is it really like on top of each other with a gap, or it is just like there is an insulator in between?
Actually, the device dimension means that the size of magnetic and thermoelectric materials, the gap actually should be as small as possible. If if these materials are directly attached to each other, the shunting effect reduces the transverse thermal power. So we inserted the MgO substrate between them. But what is important here is the size ratio between magnetic and thermoelectric materials. For example, please imagine the situation that if the thermoelectric layer is very thin and highly resistive, and the magnetic material is very large. So in this case, even when the thermoelectric material exhibits the Zebic effect, the charge current generated in the magnetic material is very small. Charge current density becomes very small. Yeah. In contrast, if the thermoelectric material is very large and magnetic material is thin films, the large charge current density can be obtained in this configuration. So this is summarized in the size ratio. So in addition to the transfer port properties, we can optimize the relative dimensions of the each component.
Okay, thank you. One more question in that very nice slide where you have summarized all those materials and the spin-Seebeck coefficients. So, like, what is the future? I mean, how you want to improve these the coefficient, the spin-Seebeck coefficient? What would be the approach? Because as you said, the saturation magnetization is not the parameter which completely controls. So, what one should look at that when you take a new magnetic material, like it's anisotropy, it is the saturation magnetization, has there any relation to the Hilbert damping or any other material properties? So which one should look, to choose the right material?
Yeah, actually, this is very important question, but difficult question. So, yeah, at least there is no clear correlation between the anomalous nernst coefficient and the other kind of a macroscopic or static magnetic properties or other transport properties.
Okay.
So, basically, most of the recent studies focused on the band structure of magnetic materials. So, some Heusler alloys or some ordered alloys exhibit shows the very large intrinsic contribution coming from the electronic structure. But recently, actually, sometimes the experimental results is clearly deviate from the first principles calculation. And this means that other factor should contribute to the anomalous nernst effect. Of course, in a similar manner to the spin Hall effect, the extrinsic contribution coming from the impurities should also be important in anomalous nernst effect. Yeah, in this sense, there is no clear experimental guideline to further improve the anomalous nernst coefficient. So yeah, actually the systematic investigation is important.
Okay. Okay. Thank you so much. Are there questions by any other?
Yeah. Yes, I have.
Oh, Bruce, please go ahead.
Yeah. Thanks for the nice talk. I have just a question regarding the thermoelectric material and ferromagnetic material heterostructure. So in thermoelectric, we have a material bismuth selenide, which is also having topological property and good thermoelectric properties. What about your comment of that?
So you mentioned on the STTG, right?
Yeah.
Yeah, it's a very, very good question. Actually, in STTG, the total macroscopic transport properties of thermoelectric material is important. So, actually, the topological band structure is not directly related to this phenomena. But if the topological band structure contribute to the to exhibiting the large Zebic coefficient, which is important for the STTG, and here, yeah. So can I
Yeah,
continue?
please continue.
Yeah. So here we also assume the bismuth telluride in addition to silicon. Here bismuth, this is one of the best thermoelectric materials at room temperature. However, the Zebic coefficient of bismuth telluride is smaller than silicon, so the saturation value of this pink line is much smaller than the case of silicon. However, some electrical conductivity of bismuth telluride is much better than silicon, so we can obtain relatively large STTG thermal power even at small size ratio. A small size ratio means that the volume of the thermoelectric materials can be reduced. So it's convenient for improving the efficiency. So can I answer you?
Yeah. So it means we can say that if you have a good thermoelectric material in the combination of ferromagnet, it is not necessary that it will give you the high anomalous nernst effect, right? If you look this data out, you got p-type silica, and yeah, if you compare BBI to TE3.
Yes, actually, the answer depends on the the parameter for evaluating the thermoelectric conversion. If the transverse thermal power, the thermoelectric voltage is important, the Zebic coefficient of thermoelectric materials is important. However, if we want to improve the figure of merit, we also consider the thermal conductivity of the hybrid materials. In this sense, since the bismuth telluride shows much smaller thermal conductivity than silicon, even in this difference, this hybrid material shows the larger figure of merit.
Okay, thanks.
Okay, Mahi, maybe a quick question.
Yeah, just quick question. So what was your initial motivation to choose this cobalt manganese gallium? Was it driven by theory or is it sort of intuitive understanding?
Yeah, this is based on the experimental results. Actually, the anomalous nernst effect and Hall effect of cobalt manganese gallium have already been reported. And we know that this material shows the relatively large anomalous Hall angle at room temperature. Which is about 10%. Yeah, which is much better than standard ferromagnetic materials. So we choose cobalt manganese gallium.
But nowadays, the theory predicts that the ahi not necessarily results in large ANE, right?
Yes, exactly. But STTG is completely different from the anomalous nernst effect. So here, the anomalous Hall effect is the driving force. So we should choose to enhance the STTG. We should choose the magnetic material showing the large anomalous Hall effect, even if the material shows very small nernst effect.
Okay, thanks very much for the clarification. Thank you.
Yeah.
Okay, so is there anyone having a quick question? If not the case, so then
can I ask a question?
Sorry, yeah, please go ahead, Sasan.
Yeah, good evening, Sensei. So I have a question from experimental side, like which technique you use to detect the voltage from STTG? Is it ishi?
Sorry, voltage detection methods?
Yeah.
Yeah, actually this experiment was done in the bus lab, a small version of PPMS, and the voltage measurement were performed by using the standard nanovoltmeter. Yeah, and this was standard DC measurement.
So which material did you use to convert it into charge current?
Sorry,
which material did you use for ISHE?
ISHE.
Inverse spin Hall effect.
Inverse spin Hall effect is irrelevant to this effect here.
Okay. So it is directly measured from nanovoltmeter.
Yes.
Okay. Thank you.
Okay. All right. Thank you. So we would like to present you a small token of appreciation. Please stop sharing your screen. I will share my screen. Okay, so do you see my screen?
Yes.
Okay, so it's a small token of appreciation from our team. I will read it for you. W2S seminar webinar series on spintronics, Mysore, Bhubaneswar, India. It takes pleasure in presenting this plaque to Professor Kenichi Uchida from NIMS and Tohoku University, Japan, in recognition and appreciation for being a valuable speaker to give a lecture on spin caloritronics and transverse thermoelectric conversion. Thank you so much, Kenichi, for this excellent talk. Next week, same time, we will be having the lecture by Professor Ingrid Martik from Dresden, Germany. And I'm looking forward to meet you. Until then, stay safe and stay healthy. Thank you so much, Kenichi. Have a nice evening. Bye-bye.
Much.
Bye.